let's figure out what the derivative of a function could be when you're at a local or absolute maximum. Of course, any absolute maximum is also a local maximum, so we really only need to figure this out for local maximums. Well, if you're at a local maximum, it seems like the slope of the tangent line there ought to be 0. And, certainly that will turn out to be the case, but we should really check the details of why it is that the derivative at a local maximum turns out to be 0. So let's suppose that we have a local maximum at x equals a, and let's figure out what could f prime of a be. Well, remember, f prime of a is, according to the limit definition, it's the limit as, let me use the other definition of the derivative, the limit as x goes to a of f of x minus f of a over x minus a. Well, this is so general, it's hard to know how this is going to help us. But one thing we can do is take this limit from each side individually. So let's find the limit as x goes to a from the right of f of x minus f of a over x minus a. Okay, well, the denominator here has to be positive because x is approaching a from the right. So x is a little bit bigger than a, so the denominator here has to be positive. What about the numerator? So the numerator f of x minus f of a, remember the hypothesis we're making is that a is a local maximum. And that means there's some interval around a where this point on the graph at a is the highest thing nearby. So that means that f of a, f of a is right here, and x is just a little bit to the right. F of x has to be less than or equal to f of a, and that's because a is a local maximum. That's what we were assuming. So this denominator here, this f of x is actually smaller than f of a. So when you subtract them in this order, you get something that's negative. So we're taking a limit of something negative over something positive. This has to be less than or equal to 0. It could be equal to 0 if the numerator shrinks small enough, then this fraction could, the limit of this fraction could be 0. But it definitely can't be positive, right? Because this negative over positive is always negative, and the limit of something negative could be 0 but can't be positive. All right, well, what happens if we take the limit from as x goes to a from the left? So again, it's f of x minus f of a over x minus a. So this time, x is a little bit to the left of a, but still, since a is a local maximum, f of x has to be smaller than f of a. So when we do this subtraction in the numerator is going to be negative. What about the denominator? Well, this time x is less than a, so when you do x minus a, when you have a smaller number minus a bigger number, you get something negative. So here we have negative over negative, which is positive. So we're taking of the limit of something that's always positive. Well, the limit of something that's always positive has to be greater than or equal to 0. All right, so on the one hand, we have the limit as x goes to a from the left of f of x minus f of a over x minus a. So on the one hand, this has to be greater than or equal to 0, right? That's this line. But this one-sided limit, it has to be equal to f prime of a, because f prime of a is the two-sided limit, but we're assuming that that existed, right? We assumed at the beginning that this function is differentiable. If it's differentiable, then this one-sided limit has to be equal to f prime of a. But by the same token, f prime of a has to be equal to the limit as x goes to a from the right of f of x minus f of a over x minus a. But what we showed up here is that this limit is less than or equal to 0. And you can see, just reading off this line, 0 is less than or equal to f prime of a is less than or equal to 0. But that means that f prime of a has to be equal to 0. So this proves that at a local maximum, the derivative of the function has to be 0. The same argument works if you are looking at a local minimum. It's just the inequalities turn around.